Hello and welcome. My name is Ted Geoffrey Ngaliana Nikodamasari, metric number 102994, and today I will be presenting and explaining a vehicle powered by a compression ignition internal combustion engine, specifically a 2011 Mitsubishi Pajero Sport 4x2 wagon with a GL variant and equipped with a 2.5 liter DID diesel engine. The vehicle you see besides me here belongs to my parents, and permission has been granted for me to record it for academic and educational purposes. Now, in this video, I will be explaining this vehicle not only from a customer perspective and performance-wise, but I'll also be explaining from an engineering and thermodynamic standpoint, because understanding how an engine works internally is just as important as how it feels on the road. The Mitsubishi Pajero Sport is categorized as a mid-size SUV, while it has off-road capability by design, especially in other drivetrain variants. The 4x2 configuration used here is primarily optimized for on-road driving, specifically highways, urban roads, and for long-distance travels. Therefore, the engine must deliver smooth operation, strong torque for overtaking, and high fuel efficiency for all while maintaining durability. The engine that powers this vehicle is a 2.5 liter DID, 4 cylinders, 8 valve, and intercooled turbocharged diesel engine. Commonly known by its engine code Mitsubishi 4D56, this is a 4-stroke internal combustion engine operating on the principle of compression ignition, which distinguishes itself from petrol engines that rely on spark ignition. The way the engine operates, from an engineering perspective, this engine is designed to operate with a high compression ratio. Now, during operation, air alone is drawn into the cylinder, is then compressed to a very high pressure and temperature, and only then diesel fuel is injected into it. Because of the high temperature of the compressed air, the fuel ignites spontaneously without the need of a spark plug. This fundamental operation principle is what defines a diesel engine. Now, during the intake stroke, the piston moves downward from top dead center to bottom dead center. As it moves down, the intake valve opens, allowing fresh air to enter the cylinder. At this stage, no fuel is present. However, the cylinder volume increases with pressure remains slightly below atmospheric due to flow resistance. The stroke prepares the cylinder for compression. Next comes the compression stroke. The piston moves upwards with both intake and exhaust valve closed. As the piston moves up, the volume inside the cylinder decreases significantly because the same amount of air is now confined to much smaller space. The pressure rises sharply though. At the same time, the temperature increases due to compression. This increase the pressure and temperature is not accidental. The increase is not accidental, that's what I meant. It is intentionally designed so that the diesel fuel will later ignite spontaneously when injected. Now, near the end of the compression stroke, diesel fuel is injected directly into the hot compressed air. This marks beginning of the power stroke. The injected fuel atomizes, mixes with the hot air, and ignites almost immediately. Combustion causes a rapid rise in temperature, and the expanding gases push the piston downward with significant forces. This downward motion of the piston is what produces useful mechanical work, which is eventually transmitted to the wheel of the vehicle. And finally, during the exhaust stroke, the piston moves upward once again. The exhaust valve opens and the burnt combustion gases are expelled from the cylinder. This completes one full 4-stroke cycle. While this description explains the movement of the pistons, engineers analyze engine performance using thermodynamics cycles. Well, speaking about that, for diesel engine, the reference model is known as ideal diesel cycle. It is important to understand that the ideal cycle is not a real process. It does not exist in any physical engine. Instead, it is a theoretical construct that allows engineers to evaluate the maximum possible efficiency of a diesel engine under perfect conditions. The engine here is also turbocharged and intercooled. The turbocharger increases the mass of air entering the combustion chamber. Meanwhile, the intercooler reduces the temperature of compressed air before it enters the cylinder, and this results in a denser air charge, a more efficient combustion, and improves torque output, and of course, a better fuel economy. From a customer perspective, this translates into a smoother highway cruising, a more confident overtaking, and lower fuel consumption over long distances. Now, to truly understand how this engine operates, we need to look inside the cylinder and examine the movement of the pistons, because piston motion directly governs the pressure, volume, and temperature changes that occur during engine operation. Now, these changes are later represented using pressure volume or PV diagrams and temperature entropy or TS diagrams. The ideal diesel cycle is based on several assumptions. It assumes that there is no friction between moving components, no heat loss to the surroundings, and that combustion occurs instantaneously and in a perfect controlled manner. It also assumes that all processes are reversible and that the working fluid behaves as an ideal gas. These assumptions allow us to focus purely on the thermodynamics relationship between pressure, volume, temperature, and entropy. To visualize the ideal diesel cycle, we use pressure-volume diagram. If you look at the PV diagram, you will see a closed loop consisting of 4 distinct processes. The first process, from point 1 to point 2, represents isentropic compression. During this process, the piston moves upward, causing the volume to decrease. Because no heat is transferred out of the system and no friction is present, all the work done on the gas increases its internal energy. As a result, pressure rises sharply as volume decreases. This behavior is consistent with the ideal gas law and the first law of thermodynamics. The second process, from point 2 to point 3, represents constant pressure heat addition. This process models diesel combustion. As fuel is injected and burns, heat is added to the system. However, unlike in a petrol engine, combustion in a diesel engine occurs while the piston is already moving downward. The increase in volume due to piston motion offsets the increase in pressure caused by heat addition, resulting in an approximately constant process of pressure. This controlled pressure rise is one reason why a diesel engine produces strong, smooth torque. The third process, from point 3 to point 4, represents isentropic expansion. Here, the high pressure, high temperature gases expand and push the pistons downward. Volume increases while pressure decreases. The energy stored in the gas is converted into mechanical work. In the ideal cycle, This process is perfectly efficient with no energy losses. However, and the final process from point 4 back to point 1 represents constant volume heat rejection. Heat is rejected from the system, pressure decreases, and the cycle returns to its initial state ready to begin with again. The same process can be analyzed using a temperature entropy diagram. In the ideal TS diagram, the compression and expansion process appears as vertical lines, indicating constant entropy. This means that there is no irreversibility and no energy degradation. Heat addition and rejection are represented by horizontal or curved lines, showing controlled changes in entropy due to heat transfer. Now, however, when we analyze the real diesel cycle, which is a cycle followed by the Mitsubishi Pajero Sport engine, we observe significant differences. In reality, compression is not perfectly isentropic. Friction between the piston and the cylinder walls converts some mechanical work into heat, increasing entropy. Heat is also lost to the cylinder walls during compression, reducing the final temperature and pressure compared to the ideal case. Combustion in a real engine does not occur instantaneously. Fuel injection takes a finite amount of time, and combustion continues even as the piston moves downwards. As a result, pressure does not remain perfectly constant during heat addition. Peak pressure is lower than predicted by the ideal cycle, and some fuel energy is lost as heat rather than converted into useful work. And during expansion, additional losses occurs due to the heat transfer and exhaust back pressure. The gases do not expand as efficiently as in the ideal cycle, and the area enclosed by the real PV diagram is smaller. The smaller area directly indicates lower work output per cycle. In the TS diagram, for the real cycle, the lines are no longer vertical. Entropy increases in nearly every process due to friction, turbulence, and heat transfer. This increase in entropy represents irreversibility, which is a fundamental reason why real engine can never achieve ideal efficiency.
At this stage, having discussed the piston motion, the ideal diesel cycle and the real diesel cycle separately using both the PV and TS diagrams, it is important to directly compare these two cycles side by side. This comparison allows us to clearly understand how theoretical thermodynamics translate into real engine operation, specifically for the 2.5-liter DID diesel engine used in the 2011 Mitsubishi Pajero Sport 4x2 GL. Starting with the nature of the cycle itself, the ideal diesel cycle is purely a theoretical and analytical model. It does not represent a physical engine, but rather an idealized reference used by engineers to study performance limits. In contrast, the real diesel cycle represents the actual operating cycle occurring inside the Pajero Sport engine during everyday driving. This immediately tells us that while the ideal cycle defines what is theoretically possible, the real cycle defines what is practically achievable. If we look at the comparison process, the difference becomes even clearer. In the ideal diesel cycle, the compression from one point to another, to point 2, is assumed to be perfectly isentropic. This means that there is no heat loss, no friction, and no entropy generation. As the pistons move upwards, volume decreases and all the work done on the air is converted directly into increased internal energy, resulting in a sharp rise in pressure and temperature. However, in the real Pajero Sport engine, compression is non-isentropic. Some of the work input is lost due to friction between the piston rings and the cylinder walls, and some heat is transferred to the surrounding engine structure. As a result, although pressure still increases as volume decreases, the final pressure and temperature at the end of the compression are lower than those predicted by the ideal cycle. Moving on to the combustion or heat addition process, the ideal diesel cycle assumes that combustion occurs instantaneously at constant pressure. This assumption simplifies analysis and results in a well-defined constant pressure line on the PV diagram. In a real engine, however, combustion takes place over a finite period. Fuel injection is not instantaneous, and mixing between fuel and air is not perfect. Consequently, pressure does not remain perfectly constant during combustion. Some regions inside the cylinder experience delayed heat release, leading to incomplete combustion and energy losses. This difference is clearly reflected in the reduced peak pressure observed in the real PV diagram. When we examine the expansion process, the ideal diesel cycle once again assumes perfect isentropic behavior. During expansion from point 3 to point 4, the high pressure gases expand without any heat loss, converting the maximum possible amount of thermal energy into work. This results in the largest possible enclosed area on the PV diagram, which corresponds to maximum work output per cycle. In contrast, expansion in the real Pajero Sport engine is affected by heat transfer to the cylinder walls and by exhaust back pressure. These losses reduce the effectiveness of expansion, resulting in a smaller enclosed PV area and therefore lower actual work output. The difference in work output is one of the most important practical distinction between the ideal and real cycles. In the ideal diesel cycle, the enclosed area on the PV diagram represents the maximum theoretical work that can be extracted from the fuel. In the real cycle, this area is noticeably smaller, directly indicating reduced engine output for the same amount of fuel energy. This reduction explains why real engines can never reach the efficiency predicted by the ideal thermodynamic models. The TS diagram further reinforced this comparison. In the ideal diesel cycle, compression and expansion processes appears as vertical lines, indicating constant entropy and perfectly reversible behavior. There is no entropy generation, and energy quality is preserved throughout the cycle. In the real diesel cycle, however, entropy increases during nearly every process. Friction, turbulence, heat transfer, and non-ideal combustion all contribute to irreversibility. On the TS diagram, this is seen as curved and shifted lines, clearly indicating energy degradation and efficiency loss. Despite these differences, it is important to emphasize that the real diesel cycle is not a failure of an engineering design. Instead, it represents a carefully optimized balance between performance, efficiency, reliability, and durability. Mitsubishi's engineering approach using turbocharging, intercooling, and direct injection technology is aimed at reducing the gap between the ideal and real cycles as much as practically possible. This results in an engine that delivers strong low-speed torque, smooth on-road performance, and good fuel economy, even though it operates under real-world constraints. This comparison between the ideal and real diesel cycle clearly shows that while the ideal cycle provides an upper performance limit, the real cycle defines the true operating behavior of the Pajero Sport's 2.5-liter DID engine. Understanding these differences allows us to appreciate how thermodynamic theory is applied in real automotive engineering. Well, in the case of Mitsubishi Pajero Sport 2.5-liter turbocharged diesel engine, it achieves a balance between efficiency, performance, and reliability. While it does not operate on an ideal cycle, its real-world performance is optimized for its intended use and delivering strong torque, furthermore, smooth on-road driving and excellent fuel economy.
In conclusion, this vehicle is powered by a 4-stroke compression ignition diesel engine operating on a real diesel cycle that deviates from the ideal cycle due to unavoidable physical losses. However, through intelligent engineering design, the engine provides reliable and efficient performance suitable for both everyday driving and long-distance travel. Thank you for watching.